the topic we're going to focus on today is conservation of energy. But before that, we have to understand the concept of Holman Transfer to explore the usage of the calculations we're going to do today. So let's explore what Holman Transfer is. Let's say there's sun in the middle. We're going from Earth to Mars. And now the question here is how to get from point A to point B. Meaning, how do we get from the Earth to Mars? How did scientists figure that out? We're going to explore what Holman Transfer is from now on. Basically, the Holman Transfer, according to Kepler's third law, states that the increase in the velocity, we're going to state that as delta V, which rocket scientists love to talk about. The increase in velocity will result in the expansion of this orbit, specifically the apogee, which is the highest point. So let's say the apogee, which is supposed to be the highest point of the orbit, is here. Well, this is a circular orbit, but there's no guarantee that this is perfectly circular, that there is no highest point. So let's say the apogee is here. The delta V, the increase in the velocity, will result in the expansion of the apogee. Meaning, the new apogee, when the spacecraft accelerates forward in this direction, will result in this kind of orbit. If you go even further, I will give you an example, a visualization of the whole process to make understanding easier. So let's say this eraser is Hermes. We start from the Earth. We try to transfer to Mars, but in order to do that, we have to increase the velocity. The normal orbit of the Hermes without accelerating would be like this. It will have the same orbit as the Earth. If it's not at an appropriate velocity, that will intercept the Mars. But if we accelerate here, if we give a little kick, then it'll increase the apogee. Notice the spacecraft goes slower in this area, but faster when it gets closer to the sun. This is how orbital mechanics work. Now, if we increase the velocity even more, to intercept the Mars gravity, the Martian gravity, and it'll become something like right? So it'll intercept Mars. And that is how we go to the red planet. In this case, instead of spacecraft, instead of Hermes just spinning around the sun, this is called an elliptical orbit, and this is called a circular orbit, since in a circular orbit, the velocity doesn't change throughout the orbit. But in an elliptical orbit, the velocity changes quite radically, since we gave a little kick here. Right? We're going to explore it further later on, but you have to remember that this elliptical orbit kind of thing leads the spacecraft to intercept the Martian gravity. So every celestial object has gravity that pulls the spacecraft inwards. So if we increase the apogee furthermore, this spacecraft is going to intercept the Martian gravity, and it will kind of jump into the Martian gravity. Like that. Instead of just spinning around the sun, it will intercept the Martian gravity. And the Martian gravity will trap the spacecraft, preventing it from escaping the Mars gravity. But we will explore this concept further, because technically it won't just trap the spacecraft, but it will do something called a gravitational slingshot. And in order to get aka trapped in Martian gravity, we have to perform a decelerating maneuver. Since the velocity here is way too fast, the velocity of a spacecraft here is way too fast to be in a safe circular low Martian orbit, it will just kind of pass by Mars and keep spinning the sun. But the thing is, it won't just pass like that. It's going to pass like this. Like this. It will change the route of the spacecraft, which is a very interesting concept. Right? But in order to decelerate, you go to the closest point you can ever go to the planet Mars, and then you decelerate meaning you have to accelerate in this direction, because this direction is going to be a negative velocity. So this direction is going to be a positive velocity. So the rocket fume is going to come out this way, because then the rocket's going to accelerate this way, a negative velocity when you think about going this way, right? So it's going to slowly decelerate and then intercept the Martian gravity. It's a little hard to visualize. So let's think about the space-time continuum. Because Sun is supermassive, it covers everything. It's a giant bucket that has Earth and Mars in it. So let's say the spacecraft kind of jumps out of the Earth's small bucket that is also spinning the Sun. Think about a marble just spinning around the edge of this bucket. It kind of jumps out of this bucket, and then it's going to, kind of get into the solar bucket, which is a larger one that covers everything. It's going to spin around, and then you give a little push to intercept the Martian gravity. Then it's going to intercept it, and then because there's a small bucket here, it is like the whole time spacecraft is maneuvering, it is in the Sun's bucket, but this time it is also in the Martian space-time continuum, which is this little bucket that, to visualize how gravity works. So it's going to spin around if properly decelerated. So think about throwing a marble inside a bucket. If you add too much velocity while you're throwing a marble inside the bucket, it will rather just bounce off instead of actually getting inside the orbit, getting inside the bucket. So that's the exact reason why we have to decelerate before we actually enter the Martian gravitational field. So we decelerate and then we enter a stable Martian orbit. And that's how orbital mechanics work. Now we're going to look at the calculations and its applications.